Okay, hi everyone. I am Takashi Ishida, and I'm a lecturer at the University of Tokyo, and also a visiting scientist at RIKEN AIP. I would like to host today's TrustML Young Scientist seminar. Before we begin, let me briefly introduce RIKEN AIP to Gail. RIKEN AIP stands for RIKEN Center for Advanced Intelligence Project, and we call it RIKEN AIP. And it was founded in 2016, so about 6 years ago, as the research center for the MEXT AIP project. So MEXT is Ministry of Education, Culture, Sports, Science, and Technology in Japan. And in RIKEN AIP, we are working on fundamental research on AI and also various real-world applications. And as one of the activities at RIKEN AIP, we are hosting a series of talks called TrustML Young Scientist Seminars, which is led by Jingfen, where we feature young scientists that are working on trustworthy machine learning and related areas. And today we are very excited to have Gail Kaplan. So Gail is a second-year PhD student in computer science at Harvard University, advised by Prof. Yaron Singer, and he is the author of many great papers. And I'm looking forward to learning about Gail's very recent work, Deconstructing Distributions, a pointwise framework of learning, which is also the title of today's talk. So if you're ready, please.
Yeah, thanks. First of all, I'm a fourth-year PhD student. I really need to update my website. That's my bad.
Sorry about that.
Yeah, don't worry about it. It's 100% my fault. I haven't updated my website for a while. I guess you're familiar with not updating your websites, or is it only me? But in any case, can you see my screen?
Yes, we can see your screen.
And you can see my cursor.
Yes, we can see it.
Okay, so it's my first time giving this specific talk, so please ask questions. I'm certainly gonna miss some points, so I really like interactive talks, so feel free to interrupt at any point, ask questions, make sure I'm honest and I'm not making any mistakes. It's important for me that the talk is interactive and that people are comfortable. So let's start. I'm gonna be talking about deconstructing distribution, a pointwise framework of learning, a recent paper that is a joint work with Nikhil, Saurabh, Boaz, and Pritam, my amazing collaborators. So let's get right into it. So the main setting is going to be supervised learning, although I guess our results can be extended to unsupervised learning. So it's a familiar setting. We have some task, for example, classifying cats versus dogs, and we get a train set, and then we get unseen examples, and we want to know whether an image is of a cat or a dog, okay? And more precisely, we have access to a list of label data points sampled from some distribution D, xi's and yi's, and we want to be good on unseen point x, xy, also sampled from this distribution. And how do we usually solve this problem, especially in computer vision? We just take a very large ResNet model or something similar, or a transformer, and plug in some default hyperparameters, try to train it, and pray that everything works well. And if we just pray hard enough, we can get really nice results. So, for example, on ImageNet, the recent papers with it's only praying, it's also a bunch of tricks, but with in a recent paper, nice paper called Meta Pseudo Labels by Google, they achieved the 90% test accuracy on ImageNet. The main idea is a distillation setting, a student-teacher setting. And then another paper called Are We Done with ImageNet in 2020, they actually compare how do the old labels done by humans compared to models labels. So we take an ImageNet image and give it a model label, an old label, and see how much new humans think which label is correct. So for AlexNet, for example, back in the day, the old labels, the human annotated labels were much better than the model labels. But as we progress in time and get to 2020 and ensemble models, which are worse than those pseudo labels, you can see that actually the models have better labels than the human annotated ones. Okay, so this bears the question: are we done with ImageNet? Are we done with computer vision? And you could say, wait, but I only have 90% accuracy. Like I can improve to 100%. I still have a lot to improve. But if you actually go and look at the data set, you see that 90% is not accurate. It's not actually 90%. So you could encounter things like basically wrong labels, because it's not a purse, it's a wallet. You can see things like this image, which is annotated with a hammer, but you could see a screwdriver and a drill and all kinds of tools here. And you have inconsistencies in labeling. So you could have a notebook and a laptop. So there are many things that actually take this 90% to be some upper bound, and going beyond that might be just learning noise. So 90% is actually great, but where are the self-driving taxis they promised, right? And the main issue that we didn't solve, in my opinion at least, is kind of long tail events where we have these weird cards that carry different cars, and they're very rare and weird, and prohibit us from doing very well on weird examples, because you just don't see them often in training. You could also see like basically weird conditions or weird lightning effects or very weird objects. And sometimes when we deploy our models, we actually expect them to perform on completely out of distribution objects. So we want them to perform well on renditions of images or sketches or objects from a different country or something like that. So instead of trying to be good on an input from D, we actually often want to do well on inputs from D hat, where D and D hat are very similar. This is called a distribution shift or out of distribution performance. Any questions so far? Okay, cool. And this out of distribution performance we can take it to even more extreme, where the task even changes. So for example, this nice paper by OpenAI called Clip, they do a contrastive caption to image matching, and they use the model later to do image classification. So you change the task, and this model performs very well on image classification, even on very weird data sets. And interestingly, this model can be useful for a generation of images and many other tasks. So we are getting further and further away from our original task, and we demand our models to be good on something that we did not ask them to do. Essentially, like we asked them to be good on distribution D, but they're performing things which are well far away from D. And a recent paper by Google called Palm, they trained you probably all saw it on Twitter, where they trained the 500 billion parameters model on next token prediction. So you just want to predict the next token, and and those models start to explaining jokes and performing all kind of different interesting tasks that are not part of their training sets. And so how do we deal with out of distribution? So there are two main philosophies. The first philosophy, kind of illustrated in the previous slide, we just train a huge model and hope for the best. And I'll talk about it more deeply. I'll categorize this under accuracy on the line, or implicit dealing with out of distribution implicit. There is also something that's probably very familiar to people in this seminar, which is called the robust optimization. And I don't want to get into details, that's not the point of the talk, but basically we're solving a min-max problem. So we want to optimize the best classifier for the worst distributions. Here U is some uncertainty set, and we want to find the best classifier for the worst uncertainty, so the worst distribution sheets, for example. So back to accuracy on the line. The main idea here is that performance on out of distribution of the performance on distribution. So in a recent paper by Recht et al., what they do is they try to measure, their original motivation at least was to try to measure how much do we have test set overfitting. Okay, so we're using the ImageNet test set over and over and over and over again. And the question is, like, how much did we overfit by doing that? And potentially you could overfit quite substantially, but they showed that this overfit is actually small, but that's not the only thing they show. So what they do is they assemble a new data set called ImageNet v2. And the main idea, if you haven't saw the paper, is that they try to match all kind of sampling that was done for ImageNet and to reproduce the creation of the data set. So they try to make ImageNet v2 as close to ImageNet as possible. So here is the x-axis is ImageNet accuracy, and the y-axis is ImageNet v2 accuracy. The dashed line is y equals x. So if we're on the dashed line, it means that our model performs equally well on both of those data sets. And all those points are different models. So that could be some ResNet, that could be some ConvNet, that could be some fully connected network. And they see this nice functional relationship between those two data sets. Okay? And the interesting part is that this functional relationship holds for all kinds of distribution shifts. So here it holds for CIFAR and CIFAR10 fog, and it holds for the YCB dataset with YCB out of distribution, and it holds for SYNC, which is like a large CIFAR10 and CIFAR10. So when you improve on CIFAR10, you have this nice functional relationship with SYNC. And another surprising fact, it holds not only for neural networks, it holds for pre-trained neural networks and random forests and the random features and nearest neighbors and SVMs and all kinds of models. Okay. Any questions on that? Okay, I'll assume that's clear. However, okay, and the conclusion from this accuracy on the line is, if we want to perform on the y-axis on out of distribution, we need to go as far to the right on the x-axis, right? So if we get a 100% model on the x-axis, we'll probably get a pretty good model out of distribution, which is sort of consistent with the previous slide where they take, or with this slide where they take the models to perform as well as possible on the original task, even if the task was pretty far away from our shifted distribution. Okay, cool. However, there is a caveat, and that those accuracies on the line, the trend doesn't always hold. for example, for this chameleon data set, you just don't see a clear trend. So you have a bunch of variants, and it's unclear what's happening here. And the authors try to explain it by a covariate sheaf and all kind of explanation, but I think it's safe to say that we don't really know why do we have some such clean trends, and some distribution shifts just don't follow this trend. Okay. Cool. So the main question we want to understand, or at least it was the main motivation for our work, is for what distribution shift does the accuracy on the line hold? When will we see it? When will we not? To what degree will we see it? To what degree will it fail? And I think the main problem is that we need to understand this for natural distributions, and natural distributions are very tricky, and it's really hard to say something about natural distribution. We're really good at saying things about models. We understand our models much better, although we're not like understanding models perfectly, but I think understanding distributions we're much worse at. So basically, how can we quantify this shift? How can we approach this shift and say something smart about it? Okay. So in this talk, I'll start by giving the pointwise perspective of learning and try to advocate for why should we care about this pointwise perspective, and how what kind of different qualities we can extract from it. Then I'll talk about crossing the line, which is going to be breaking this accuracy on the line phenomenon using our pointwise perspective. Then I'll give all kinds of interesting application to the pointwise perspective. And finally, I'll try to talk about some theoretical conclusions and other takeaways that we can learn from this pointwise perspective. Okay, so let's consider this matrix of points by models. So usually we only look at this part. So we take, like, say, ResNet 50, we train it on ImageNet, we look at the test accuracy, it's 10%, then it's 30%, then it's 50%, and it's 70%. And the points here are just serve as something that we average through. So each row here is some point, let's say from the ImageNet validation set, and each cell here is the accuracy of the model on this point. So you can ask what's the accuracy of the model on a point, and you could, like, for example, look at the softmax probability that the label is correct. Okay. And specifically, we do it for smoothing purposes. So our results are cleaner. We average it across a couple of models. For example, 10. Okay. So usually we think about a single model average over multiple inputs, but instead I'll advocate for looking at a single input averaged across the a prediction of multiple models. Is this clear?
Can I confirm my understanding?
Yes.
So the accuracy here means the softmax probability for the class that is specified the label of the train,
exactly,
of the data here.
Yes.
Oh, okay.
Yes, exactly. Okay. Yes. Sorry. Exactly. It's the basically you can think about it the probability to be correct on a label for maybe an ensemble of models. That's one way to look. And the ensemble here mainly serves to be to smoothen out noise, because the problem with pointwise frameworks is it's very noisy. So we have to smoothen it out a little bit so we have interesting conclusions. Okay, cool. So if we look at one row of this Dalmatian and we look at this one row, and instead of looking at those values, I can look at the whole stack plot of softmax probabilities. So here each stack in the stack plot, so each layer here is a different class. So the blue class is the Dalmatian, the purple class is the soccer ball, the pink class is American Staffordshire, etc., etc. So we have all 1,000 ImageNet classes here stacked on each other, okay? And that's the softmax probabilities, the softmax probability to be correct, okay? And here, for example, we see a 30% model, 30% model, and the y-axis, it's not annotated, but it's 0 to 1. It's a probability to be correct, okay? Oh, and the global accuracy is the accuracy of the model, as I mentioned before. And you can think of x-axis as so why do we talk about accuracy? Why don't we talk about training time or a number of samples or model size or something like that? And basically, we want to think about the x-axis as resources. And there are many papers like the double descent or the deep bootstrap and the scaling law papers that show that you can basically increasing in different axes of resource improves accuracy in a very similar fashion, okay? So as I increase my resources, I want to think about my pointwise profile. Okay, cool. And you can see that a lot of interesting things are going on here, even in this simple profile on this one image. And you can see that the simple model is like a weak model that gets 30% accuracy, classifies the image correctly as a Dalmatian, but then as training progresses or as our model becomes stronger, it actually thinks that the image is of a soccer ball. So we can learn a lot about what happened in learning from this image. So we can one way to think about it, and I'll elaborate on it in a moment. We can think about it as accuracy on the line for one sample. And note that it works both for in distribution and out of distribution inputs. And often we just care about individual points. So if our model failed to classify pedestrians on a crosswalk, we want to understand why, what happened, what's the issue, and it could serve as a mean of debugging. So let's look at a couple of profiles. Hopefully you understand what a profile is. If not, please feel free to ask questions, unmute yourself and ask questions. But now we'll see a couple of profiles to get a feeling of what is happening. So the first kind of profiles that we observe when looking at ImageNet is easy point profiles that the local accuracy, the point accuracy shoots very quickly to 100%. So even weak models are very easily classify those objects correctly. And here we have an ImageNet image. And here we have an ImageNet R image, which is a rendition of images. So here we have a drawing of a bus, and it's an out of distribution input. However, our ResNet is able to classify it as a school bus pretty easily. So although it's not an in distribution image, it's still getting classified very easily by our model. So any questions about the profiles? Okay, feel free to ask if something is unclear. On the other side, we have hard points where the model is never able to actually classify the point correctly. So our top class stack plot is not never goes above a certain threshold, and this could be because the object is small, or because it's some weird fox squirrel balloon, which I wouldn't be able to classify correctly, maybe. So here again, we see an ImageNet image and an ImageNet v2 image. We talked about ImageNet v2, it's a resampled image. Okay, so the easy points and the hard points are kind of obvious. There are lots of examples of lots of papers about example difficulty. But let's get to more interesting profiles. So here we see this image of corn, which under low resolution might look like a honeycomb, right? So if we look at this, at the profile of this image, we see that it was pretty certain here that it's a honeycomb, and then it gets less certain about it. And here it was more certain that it's a corn, and it got also less certain about it. And then it actually, eventually the stronger model gets it right. So what we see is that the certainty of the model decreased, which we call entropy non-monotonicity. So the entropy of the predictions increased. So we have higher entropy here than here. So we're non-monotonic in entropy. And here, this is adversarial images. ImageNet A, many classifiers are really bad on this data set. It's a very challenging data set. It's natural images. It's not adversarial in the sense of adversarial attacks. It's just adversarial in the sense that many images here are very, very hard for classifiers. And for various reasons, feel free to check this data set. So although the cat here kind of occludes the image, we see accuracy non-monotonicity. So here the accuracy was really high, and then the model starts getting worse accuracy here. So we can be non-monotone in accuracy, and we can be non-monotone in entropy, and it can happen both for ImageNet images and for ImageNet and for out of distribution images. Another interesting profile is compatible points. And the compatible points basically follow this y equals x line. So your improvement, your global improvement corresponds to local improvement. So as we improve on our in distribution, we improve on some point. And a priori, you could expect all your points to look hard and easy or something like that. And then it would average out to accuracy on the line to have like some y equals x, but actually there are compatible points, which I find really cool, that they followed the improvement on the distribution. So and even more surprisingly, maybe, that even severe out of distribution shifts can follow this pretty closely to the y equals x line, and could be considered compatible. So basically, to summarize, we can quantify distribution shift by how many points of each type we have. So and I'll get to it in the next section. Okay, cool. So any questions?
Can I ask a few questions?
Yes.
So you showed us four categories: the easy, hard, and compatible, and the non-monotone one. Is it possible
Yes.
to somehow figure out the proportion or of the test data set?
That's a great question, and that's basically kind of what was my summary. I agree that it's a bit qualitative right now, and we wanted to do this quantification, but I remember, for example, that the number of hard points. So the problem is that you need to choose some threshold, right? And for example, I choose a threshold for hard points to be never rising above 5%, okay? And then about 5% of the images never go above this threshold. But then this threshold itself is a bit qualitative. So you could try to quantify it, and but it still will be sort of qualitative.
Right.
That's why I didn't show this quantification. But yeah, it's a great question. We're thinking about it, and it's a good point to wonder about.
I see. Thank you. Another question is, I think you showed us the example with the soccer ball,
yes,
and Darmashan, and it seems like the original image is like a multi-label rather than a single label image. And the example that you showed us about the corn is somehow similar, that it has label ambiguity. So do you have any comments about or thoughts about the relationship between like those kind of topics?
Yes, so the corn doesn't have label ambiguity. It's just corn. I like maybe if it was I know it's like it even can confuse a human, but it's actually just corn, and you can see that the model treats it as if it had label ambiguity. And here I agree with you. It's a label ambiguity, and maybe there is no good way of solving it. And my speculation is that the models actually here learn that often soccer balls are on grass, or maybe it's more prominent in the picture or something like that. So that's how the soccer ball wins. But yeah, basically that's exactly the point. Like you're asking the right question of okay, like we have label noise, like we have label ambiguity. What is even right? And that studying the profile actually like gives you this information, like lets you know, okay, your model is not being wrong, it's actually being right, and yeah, and you could also learn like how it thinks in some sense, because like as the learning progressed, it moved its prediction from Dalmatian to a soccer ball. So you can understand kind of like its process of learning.
Yeah, it's very interesting. Okay, thank you. That's it for me.
Great. Any other questions? Great question so far. So I'd be happy to take more questions. Okay, so I introduced this pointwise analysis, and it could be, we've seen a little bit that it can be useful as a conceptual way of reasoning about learning, but it could also be a practical tool for revealing structure in learning models and datasets. So I'll start with the datasets part. So here we reproduce the rect et al. Experiment with ImageNet v2 and ImageNet. So we have these three models: ResNet, DenseNet, DenseNet, larger DenseNet, and we see that all those models throughout training fall on this nice linear, or not linear, monotone trend. You have this really nice correlation, no noise at all, just amazing. And if you just look at the dogs subclasses, so ImageNet has like 150 or something dog subclasses, and you look at how ImageNet accuracy corresponds to ImageNet v2 dogs accuracy, you see a slightly different trend, not exactly the same trend, but also a very clean trend. And it's interesting because a priori, classifiers with very similar accuracy can have very different accuracy on dogs. And we can even further zoom in on one image, okay? And here we see this soft probability as we saw, and we see that even for one image, you can see this nice kind of a trend. And then we zoomed in, and we got this softmax profile. So if we go back and we average those profiles, we can get, if we average them across all dogs, we'll get this dog's profile, dog's accuracy on the line. And if we average it across ImageNet v2, we'll get this ImageNet to ImageNet v2 correspondence. So one question you might ask, so we went from here to here by zooming in. The question we can ask is, can we zoom out? So what do I mean by zoom out? Instead of having this nice trend, can we create a distribution shift with some arbitrary trend? Can we create a distribution shift where, for example, the original performance is related with out of distribution's performance negatively? So here the performance is positively correlated. When I improve on ImageNet, I get improvements on V2. Can I get a trend that looks something like that? If anyone has any ideas, I would be happy to hear. Okay, cool. So I'll give you a hint, or rather, I'll explain you like how we do it. What we do is we take a lot of scenic 10 points like this one. They're lower resolution than ImageNet. They're basically like a larger CIFAR data set. And we take ResNet 18 and look at their profiles, okay? So we have a bunch of profiles for all of those scenic 10 points. And then we look at points which have non-monotonicity, which look like that have this decreasing curve, okay? And we take a data set and we choose just those non-monotone points. And in order for us to not have label noise, in order to not cheat, we remove points using clip. So if the model, if clip, which is a very strong model, disagrees with the label, we filter those points out. So we take a lot of non-monotone points, we remove points using clip, and that's going to be our data set, which we call CIFAR 10 neg. Okay, and that's how some samples from CIFAR 10 neg look. So if you saw CIFAR 10 images, that's basically how they look. A bit ugly, a bit blurry, but overall, if you squint a little bit, you can classify those images. Cool. And when we look at the CIFAR 10 neg data set, which consists of, if I'm not wrong, 1,000 points, like 100 from each class, you can see that it will follow this interesting negative monotonic, you'll have this negative monotonic curve. So here you'll have improvement on CIFAR will correspond to getting worse on CIFAR 10 neg, which I find amazing. So if we improve 30% on CIFAR, it will hurt us 40% on CIFAR 10 neg. And it breaks the accuracy on the line very strongly, because not only you have like the data sets that they found were like a lot of variance or not a very strong curve, but having a negative, so improving on one data set makes you be worse on another, means that like something is very, very weird is happening, right? You're in some sense very not optimal. And notice that we filtered those points for ResNet 18s, but it had the same effect for DenseNet 121. So the architecture didn't change the fact that this trend was negative. Any questions about that? Cool. I'll get back to CIFAR10 for a little bit soon. So what we did so far is we introduced this pointwise perspective of learning. We saw how we can break this accuracy on the line trend, and now we'll see some other applications of this pointwise perspective, and we'll conduct a more systematic study of the structures of profiles, and we'll try to understand what can we learn about training procedures. And so far we saw what we can say about the data set, and now we'll see what it can say about our models. Okay, so let's look at those two CIFAR10 images. And here we have two models, ResNet and DenseNet, and we have two ways of training them. One is from scratch, and the other is pre-training them on ImageNet. So we just resize ImageNet to 32 by 32, pre-train the models on ImageNet, and then fine-tune it on CIFAR10. And when we look at the global accuracy versus point accuracy for those images, we see that the from scratch models behave very similarly, and we also see that they behave differently. Maybe a bit qualitatively, they behave differently from the pre-trained models, and we also see that the pre-trained models eliminate this non-monotonicity. Okay, and now we try to quantify that, and we introduce some sort of notion of distance, which is not very important, but you can think about it as pointwise L1 distance of profiles. So I just sum the absolute differences of each point on the profile. So discretize the profile, or discretize two profiles, and sum their pointwise differences, the absolute values. And then we can see this nice confusion matrix where the architecture doesn't really affect the profile that much, but pre-training affects the profile a lot. Okay, so pre-trained models behave distinctively differently from scratch models. How do they behave differently? We touched a little bit upon that, and basically we introduced this non-monotonicity score. Again, it's like the distance score. It's very natural, it's very simple. It's just some sort of integral of the negative slope. So we just look how many times you had like a negative slope. So how many times your like how many, like if you have a point here and a point here, how much did it decrease? If it didn't decrease, we don't count it. That's the basic idea of our score. And we can see this is some sort of histogram which shows how many points are above this score. So for example, let's say that the threshold for non-monotonicity, where non-monotonicity is high, is 0.1, then about 5% of pre-trained models have non-monotonicity higher than 1, and above 30% of from scratch model have non-monotonicity higher than 0.1. So pre-train reduces non-monotonicity quite substantially, and it applies both for accuracy non-monotonicity and entropy non-monotonicity. So both for whether the prediction is right and whether the model is certain about its prediction. Okay. And I know this plot is a bit confusing, and it takes some time to parse it, but basically think about the fact that 30 points have score larger than 0.1 here, and like a tiny fraction has a point, have score that has score larger than 0.1. So almost all pre-trained models are very monotone profiles, whether the from scratch models have a lot of non-monotone profiles. Okay, cool. So if we're going back to CIFAR 10 neg, we see that our points which were non-monotone here, they become monotone, and it affects the distribution that we constructed based on these points. So if we look at the DenseNet and ResNet, we see that it actually has a nice line. So you can think about it as two things. One thing is that pre-train helps reduce all kind of irrationalities of suboptimalities in the training. But you could also see it as a validation that CIFAR 10 neg is actually a valid data set, and something weird is happening in the training here. So when we train models from scratch, we actually have something somewhat of, you can think of it as a wrong prior or something like that. So to summarize, pre-training reduces non-monotonicity, both in terms of accuracy and entropy. And one important note is the only difference in pre-training is the initialization. So it's the same model, we just initialize it differently. They're both ResNet 18 and DenseNet 121. So the only difference is initialization. And this initialization gives you this better prior thing. Okay. Any questions about the pre-training? Okay, cool. I'll proceed. Okay, so let's try to see whether we can extract other insights from those profiles. And we talked a little bit about it in with the Dalmatian and the ball, but here we have a coffee mug with a drawing of a Dalmatian. And if we look at it, the model first classifies it as a Dalmatian, and then eventually it gets that it's a coffee mug. And if we do the counterfactual and actually color the cup as black, we see that that the model is, even with weaker models, are able to classify the cup as a coffee mug. And what this means is that, in some sense, lower accuracy models are more sensitive to local features than the global shape of an image. And higher accuracy models are basically more like humans. They tend to look more at global features and how does the shape look rather than the texture and color. And we can even do some synthetic experiments and give it all kind of random images. And you could see that you can find, for example, the shower curtains are the model uses kind of this grid structure to classify shower curtains, at least weaker models. And you could also see that here you can also see the shower curtains and I don't know, wardrobes and closets. Maybe it uses colors or some sort of interesting patterns. Cool. So we talked a little bit about how can we use those profiles, and now let's talk a little bit about theory, or rather, where does the theory that or theoretical models that we have fail, and we'll talk a little bit about other takeaways that we can take from profiles and future work. So recent works proposed the simple theoretical, you can call them even toy models, to explain, predict deep learning phenomena. So for example, accuracy on the line by Recht et al. Suggests this skill model, which I'll talk about, which explains accuracy on the line. And it's a very, very simplistic model, nothing too fancy, but if this model, like this model is clearly false, but if it would be correct, it would explain accuracy on the line. And there is the partition model of Bahri et al., which explains scaling laws. I don't know if people are familiar with scaling laws, but the basic premise is that neural networks, when you increase resources, they behave often like power laws. The performance behaves like power laws as of the resources. And we'll also talk about another toy model called the idealized Bayesian model. About the scaling laws. They introduced this partition model, which would explain scaling laws. And again, it's a very simplistic model. And also we'll talk about the idealized Bayesian model, also a very simple model that could explain certain phenomena in deep learning, but we'll see that in some sense it breaks, at least for when training from scratch. So we'll give some informal descriptions and see how this model breaks. And basically, it will mean that when we develop a good theory of deep learning, it will have to account for the pointwise perspective. So I'm not trying to say that those models aren't true. It's kind of clear that they aren't true. My main point is when we develop a theory of deep learning, it has to account for those pointwise perspectives. Okay, cool. So what is the skills model? It's a very, very simple model. Each point has some difficulty. So it's a one-dimensional number. So this point is easy, so it's here. This point is harder, so it's here. This point is very hard, so it's here. And the model has some skill S. So a ResNet 18, for example, is a weaker model, so it's here. ResNet 50 is a stronger model, so it's here. And if S is larger than the I, the model is correct on the point. Again, obviously, this is not true for deep learning, but a ResNet 18, for example, would be correct on this point, and a ResNet 50 would be correct on both of those points. And when we get a stronger model, either by giving it more samples or making the model larger or train it for longer, it would correspond to having higher skill. And what we saw is that we have non-monotone profiles. So the skills model cannot exhibit accuracy non-monotonicity. Another thing that the skill models has to exhibit is a universal example difficulty. So if a model is stronger, basically all models agree on example difficulty. You can't have two models that one is stronger than the other, but it has a higher difficulty for some certain examples. And we saw that, for example, here we saw that stronger models can have different agreements on different examples. Okay, so this skills models breaks. Similarly, a partition model is basically, you can think about it as a nearest neighbor in some space. And when we increase resources, we have a finer partition of the space. So imagine I get more and more samples. So my space gets more and more partition, more smooth, and my predictions get better. And it's approximately accuracy monotone. So getting more points should only improve your accuracy up to some label noises, etc. But again, we see that you have to be you have your model, your theoretical model has to account for accuracy non-monotonicity. Similarly, the Bayesian model, you have a known probability vector of the word. So think about this as a label for some example, and we want to predict y, and we start observing zi's. So for example, we get more and more samples or some other observations of the word. So our model is getting better and better, and we are able to predict y better and better. So I know I'm going about it a bit quickly, but the main idea is that this idealized Bayesian model, which would correspond, for example, for Gaussian processes with correct prior, you'll also see accuracy and entropy monotonicity. Again, the details are not very important. It's just like three very simplistic models of the world, and people give them as certain examples of trying to explain simple phenomena in deep learning, interesting phenomena that happen in deep learning. And we can see that all of them fail to account for the pointwise perspective. That's kind of a quick overview of this of the point I'm trying to convey. So I'll conclude my talk with takeaways and open questions. So real inputs are rarely drawn for a well-specified distribution. So we don't really know where those like we can't actually pinpoint the distribution of natural images, and we often even might care about individual points. So having this pointwise perspective can be really helpful for both of those things. One question that we haven't studied in this paper, which I find very interesting, is how does the choice of train set affect test points? So basically, all we did is we fixed the training procedure, and we saw that how does the test profiles behave, but it's unclear at least now, and I think it's an interesting open question to actually change the training procedure. So one thing we changed was the pre-training or model architecture, but you could change many things and study how much does it affect test points. And a recent interesting paper by Ilias et al. From Madrid's lab touch a little bit upon that. I really encourage you to read it. It's a cool paper. Another interesting open question is how do we fix irrational behavior, like this non-monotonicity? And we saw that pre-training often helps, but why does it help? It's unclear. When does it help? For which points it doesn't help? It connects to the question about label ambiguity. How do we deal with that? And finally, I rushed a little bit over the theoretical model, but the main point is when we build theory, we want, even if it's a simplified toy model, it has to be consistent not only with global phenomena, but also with pointwise phenomena. So it has to account for, for example, for the fact that when you're pre-training, you don't have non-monotonicity, and when you do from scratch, then you do have non-monotonicity. Yeah, I think that's it. I'd be happy to take questions.
Thank you, Gail, for the very interesting talk. So if anyone has any questions, please. So I want to ask if you looked at the profiles for training data. I'm not sure if it will be meaningful, but I was wondering what it will look like.
Yeah, that's a good question. Yes, sorry, go ahead.
My guess is that it might look like the profiles for the easy test samples. But yeah, I'm not sure. I was wondering what it would look like if you already saw some of the examples.
Yeah, we haven't done that. Like, you do know that eventually it has to end up in the 100%. Unlike the test examples, which you in some sense might never classify correctly. The training samples you will eventually get right as your resources grow. But you still can have ambiguity, and you can still have very weird examples which So for example, assume you have two examples which are the same but with different labels. Then what kind of profile would you get? I'm not sure. So you have the same X twice with two, like once as a dog and once as a cat, and both in the trained data set. I don't know what will happen. So we haven't looked closely at training data. We mostly focused on test data, but I think there is definitely potential for interesting things happening there as well.
I see. Thank you. Another question or maybe a comment about the pre-training part. I thought the experiments were very interesting. That like even after you align the global accuracy, like did this kind of thing happen? So what were you expecting this kind of results, or was it also not surprising for the authors?
Yeah, it was super surprising for us. Like we know that, like we did those experiments knowing that pre-training sometimes does weird things for the accuracy on the line phenomenon. So we expected that we'd see like some difference in behavior, but we didn't expect it to be this stark. You know, we expected that maybe like mild change, but we didn't expect it to have like. Basically, you look at this slide and you think that this is like two different words, right? It's like completely not in the same stratosphere. It's just so the reason I even have two plots is because you can't overlay them. It looks too weird. Yeah.
I see. Okay.
So yeah, so we were definitely very surprised by pre-training, and again, this pre-training is just different initialization.
Right. Very, very interesting. Okay, so if anyone else has any questions. Okay, if not, let's thank the speaker. Thank you very much, Gail, for the very interesting talk.
Thanks for having me. It was fun.
Thank you. So I would like to end the seminar. Thank you everyone for coming.